Welcome to Professor Ahilaa Maths, Plus 2 Mathematics, Tamil Nadu State Board Syllabus, Chapter 1, Application of Matrices and Determinants, Video 1.2, Definition 1.1, Theorem 1.1, Example 1.1. 1.2. Inverse of a non-singular square matrix. How? What is non-singular matrix? Consider a square matrix A. If find the determinant of this A, okay. If determinant A equal to 0, then the matrix A is said to be singular matrix and hence A inverse does not exist. Suppose determinant A not equal to 0, then this matrix A, capital A, is said to be non-singular matrix and A inverse exists. Keep it in mind that only when determinant A not equal to 0, in A inverse exists. That is, any non-singular matrix alone get its inverse. So, every non-singular square matrix is invertible. So many words there. Okay? Fine. Got it? Definition for inverse of a square matrix. For a given square matrix A, if there exists another square matrix capital B of same order such that AB equal to BA equal to I, then B is called the inverse of capital A. That is, B equal to A inverse and vice versa. That means we can say for B, A is the inverse. For A, B is the inverse. Okay. Formula to find inverse of a square matrix is A inverse equal to 1 by determinant A into adj. What is adj? Adjoint of A. Adjoint of a square matrix. Let us recall few terminologies before going to adjoint of a square matrix. Consider the square matrix capital A of order small n. First of all, we see minor of an element. Minor of an element small aij equal to capital Mij. That is the notation. Now see, the determinant value of the submatrix of order n minus 1 obtained by deleting the corresponding ith row and jth column of the element small aij of capital A. Capital A is of order small n. So by deleting the ith row and jth column of the matrix, we get a submatrix of order n minus 1. Order will be reduced by 1. So that determinant of that submatrix will give you the minor of that particular element small aij and it is represented by capital Mij. Got it? Let capital A equal to, let us consider a 3 by 3 square matrix with the elements 1, 2, 0, minus 1, 3, 1, minus 2, 0, 5. Now, how to get the minor of A23? That is capital M23. Minor of A23 is represented as capital M23. How will you get it? Oh. Now, what is A23 of this matrix? A23 means the element got at the intersection of the second row and third column. See the red element, that is 1, that is A23. Okay, now how to get the minor of this element? Now we need to remove the second row and third column. So it is highlighted by yellow marks. So removing these second row and third column elements, we will be getting a determinant that is called the minor of this A23. That is determinant 1, 2, minus 2, 0. Now I hope you know how to get the value of this determinant. We multiply the principal diagonal elements 1 into 0 and in the other multiplication it is negative sign. So minus of minus 2 into 2. So you'll be getting the answer 4. So the minor of A23, that is capital M23, is 4 here. Remember, keep it in mind. Now cofactor of small aij. It is represented by capital Aij. Please don't confuse. Minor is represented by capital Mij, cofactor by capital Aij. Cofactor of an element is that is the product of the minor of the particular element and minus 1 power I plus j, that is the sum of the row value and column value, that I plus j. Simply saying capital Ij equal to minus 1 power I plus j into capital Mij. So cofactor of A23 in the previous example is minus 1 power the sum 2 plus 3, and the minor of A23 is M23. So minus 1 power 5 into 4. Already we know we have got the minor of A23 as 4 in the previous slide, and so we substitute that value as 4 here. So minus 1 power 5 minus 1 into 4, that is minus 4. Got it? Now the important property discussed in your syllabus is, see the notation, small ai1 into capital J1 plus small ai2 into capital J2 plus etc. plus small in into capital Jn equal to, it is the value goes as determinant A if I equal to j and it is 0 when I not equal to j. I hope you all know the notation. Small letter represents the element and capital letter A represents the cofactor of that particular element. Okay. So the definition 1.1. Let capital A be a square matrix of order n, then the matrix of cofactors of capital A is defined as the matrix obtained by replacing each element small aij of capital A with a corresponding cofactor capital Aij. The adjoint matrix of capital A is defined as the transpose of the matrix of cofactors of capital A. It is denoted by adj. So simply remember, cofactor of an element small aij is capital Aij. When we replace all the elements by the corresponding cofactor elements, then we will get a cofactor matrix. The transpose of the cofactor matrix is called the adjoint matrix. Okay. Now adjoint of a square matrix capital A is already as per the definition previously defined, adj equal to capital Aij. This is the cofactor matrix, the transpose. So transpose of the cofactor matrix. But we know capital Aij, that is the cofactor, we write as minus 1 power I plus j into capital Mij, the transpose. Clearly, see adj equal to, when we consider the minors, we will replace the cofactor matrix elements in the matrix at each element. So considering minus 1 power 1 plus 1, that is even power, so it is plus, into capital M11, the minor of A11. Similarly, you get all the cofactor elements and that cofactor matrix, its transpose. That is equal to, suppose you are writing in the cofactor notation, means capital A11 in that pattern, the whole transpose. So just the transpose means we will revert the matrix such that rows into columns and columns into rows. So we will be getting the adj capital A equal to A11, A21, A31, A12, A22, A32, A13, A23, A33. Please have it in mind how to write it in the minor form and in the cofactor form. The notation differs. Once it is added, we multiplied with the sign of that position value, then it will turn to cofactor matrix. Got it? Now theorem 1.1. For every square matrix of order n, A into Adj equal to Adj into A equal to determinant A into In, where In is the identity matrix of order n. So we need to prove this. Now consider some simple 3 by 3 square matrix capital A. So by the property, already we have seen the property. See the property mentioned previously. Using this property, suppose I equal to j means the value is determinant A and it is not equal means 0. Keeping this property in mind, when we will have this all values. So when we multiply capital A into Adj, see the first matrix is capital A. Here we write by small letters, remember, and Adj means the transpose of the cofactor matrix. So already we have seen, so the cofactor matrix transpose. So when we multiply, simply remember the diagonal elements alone get the value determinant A and all others will be 0. So when we take this determinant A outside, it will be get multiplied by the unit matrix I3. Okay, so we are getting determinant A into I3. Similarly, when we commutate the product Adj into A, the same way, first we write Adj, that is the transpose of the cofactor matrix, into the given matrix will again give you this result. Okay, so we are getting two equations. By equations 1 and 2, it is simply proved that capital A into Adj equal to Adj into A equal to determinant A into I3. Now a note is given in your textbook. If capital A is singular matrix of order n, then determinant A equal to 0 and so A into Adj equal to Adj into A equal to 0 matrix of order n. So it is very obvious, no? Determinant A equal to 0 means, see the previous theorem. So the answer will be determinant A into I3. So determinant A goes 0 means 0 into I3 is I3 into 0, that is 0. So we will be getting a 0 matrix. It is not simply a 0 number, because multiplying two matrices, the resultant will be again a matrix. So we will be getting a 0 matrix of the same order. Okay. Now example 1.1. Simply the previous theorem, we need to prove this by this example. Okay. So we are given a matrix A. So take down the matrix A. Now we need to find determinant A first. Okay. So determinant A, see, determinant A means we can expand by any row or column. Simply keep it in mind. It is logical to expand by any row or column, but usually we prefer the first row. Okay, so here I have preferred the first row only. So 8 into, how you are multiplying? When we delete the first row and the first column, the corresponding row and column will be getting a minor, and 7 minus 4 minus 4 minus in 3. And how to get this determinant value? See the blue arrow, we multiply 7 into 3 and minus of the red arrow. Okay, so you will be getting these values. You know how to get the determinant A. Please make it practice. Now keep this determinant, that is A matrix, in mind. So you know how to find Adj. See, the minor cofactor of 8. What is the cofactor of 8? That is minus 1 power 1 plus 1, that is plus, into its minus. 7 into 3, 21 minus 16. Similarly, each place value minus 1 power I plus j into its minor. So you'll be getting this one and you are getting all the values. See, we are getting 0, 0, 0. Already we have got determinant A equal to 0. So we are proving that these are A into Adj into Adj into A equal to 0. We are getting null matrix of order 3. So the result is proved. So this third video contains our definition of inverse matrix of a square matrix, definition 1.2, theorem 1.2, theorem 1.3, example 1.2, example 1.3. Okay, so please keep revising, write and practice all the problems and definitions very thorough it. Stay tuned. Success is ours.